Okay, I'm going to fully derive the equation for the moment of inertia for a solid cylinder. So we're going to start with two fundamental things. The average density is equal to mass divided by volume. You should know that. And we can also define the moment of inertia for a particle, for a single particle. It's just denoted as I equals mr squared. We know that similarly, I is equal to the sum of all of them, like this. So that's it. Those are only two things we're going to have denoted as. So we're going to say the resistance to change with small masses. So we're going to say for infinitely small, we're summing over all of the mass. So we're going to say here the moment of inertia is defined as a triple integral for the volume of r squared times that infinitesimal differential element dm. So now how do we change dm to dv? Well, here we have rho is equal to m over v. Let's look at this infinitesimally. Your rho is dm over dv. So that means dv times rho is equal to dm. This allows us to rewrite this as triple integral of rho r squared times dv. Great. Okay, now what do we do next? Well, let's evaluate this. What is dv? dv, the differential volume element, is just some thickness base, or some thickness, then you have the arc width, and then you have the height. So we can now look at it like we'll say 0 to h, 0 to 2 pi, and then we have 0 to r of rho r squared, and then the differential element we have r dr, d theta, dz. Now let's combine the r squared and r cubed, r squared and r here to make r cubed, and then we can take out rho because it's a constant, and we'll evaluate each integral. So we have rho 0 to h dz. I'll do it like this. And then we have 0 to 2 pi d theta. And then we have 0 to r of r squared r dr. Now let's evaluate this. The integral from 0 to h of dz is just z evaluated h, so that's just h. The integral of d theta is just theta, so we have 2 pi. And then the integral of 0 to r of r squared r dr is r4 over 4. So that just simplifies to rho times h times 2 pi times r to the 4th over 4. And we can see that this 2 and this, the 2 cancels. That leaves you with rho h pi r to the 4 over 4. have to do is, okay, so we have this. This is the final answer. This actually works. This is completely, oh, I didn't even simplify the 4. Should be this. Okay, this is technically the correct answer, but we can further simplify this. Recall that we let rho equal to mass divided by volume. So can we rewrite this? Volume for this is just going to be m divided by the volume, which is pi r squared h. So now we can rewrite this as I is equal to m over pi r squared h times h times pi r to the 4th over 2. This r squared cancels, this goes to r squared, this pi and this pi cancel, this h and this h cancel, and that gives us a final answer of I is equal to 1/2 m r squared. So that is the full calculus derivation.